your video or your presentation.
Yeah, all I see right now is my first slide. It covers the whole page right now, a whole screen. So I don't see anything else.
Okay.
That's where it's going.
Gentlemen,
And
we are
everybody,
on air. We are on
right?
air. All right, everyone, welcome, and thank you for joining the 8th Global CAISPN call. We are the California International Spaceports Network. We are an international network of spaceports for business development, sharing ideas and technical queries. Tonight's call is going to be on space communications, technologies, and applications to spaceport business. Our presenter tonight is Mr. Patrick Bartholow, an expert on Moonbounce technologies. His presentation will be on technologies. We will then have a panel of experts to discuss technologies and applications for Spaceports business. We have with us Mr. Gary Barnhart from CAISP Inc. We have Mr. Eric Becknell from Radio Bro Corporation. And we have Mr. Aaron Harper from Isuru Farms. All right. Patrick, I'm turning the floor over to you. Go ahead, please. Patrick, comm check. We appear to have lost Mr. Bartholow. Yep, we have lost Mr. Bartholow. Stand by. Recalling. All right, gentlemen, so what we are waiting for Mr. Bartholow to come back. A brief introduction from left to right, if we may. Mr. Barnhart, if you may speak to your involvement in space communications.
Yes, my company, XISP Inc., or Extraordinary Innovative Space Partnerships, is involved with a mission dealing with interoperable network communication architectures, which is basically trying to evolve delay and disturbance tolerant networking capabilities as part of the broader context of creating quality of service based routers, which can be used to support pervasively networked quality of service gateways that can be used for both Earth-facing applications, on-orbit applications, and beyond Earth orbit applications. So that's that is our main main tie and focus in those regards, and we have multiple missions which are seeking to use those capabilities, both for in those three regimes. Over.
All right. Mr. Becknell, on to you.
So, my name is Eric Becknell. I'm with a company called Radio Bro Corporation. We are a product manufacturer, and we have launched a product line to support rapid development of satellites. And the first product in that product line is a communication module called Mini-Satcom. Concept is to enable people with more traditional small satellite missions to be integrated and ready for launch quicker than the available options on the market before our product.
All right.
Hey guys, I'm back.
Okay, Patrick, sound check good.
It's weird. I had my hands off the computer completely right at the time we were going to start. My computer crashed, so I had a cold reboot, and I still have to bring up the PowerPoint. But I'm basically here. Stand by.
Okay,
Or
acknowledge.
go ahead and talk whatever you need to, but I'll be probably ready in a couple of minutes.
Patrick, we're giving intros. I'll turn over to Aaron and then turn over to you, and you'll have the floor for the presentation. Okay, Aaron, go ahead.
I'm Aaron Harper with Isuru Farms. We are a research group specializing in situ resource utilization, but we've done a variety of projects ranging from a mechanical counterpressure spacesuit to software-defined radio designed for CubeSat reception, and so on, mostly having to do with the ground segment of the communications link.
All right, thank you, Aaron. All right, Patrick, on to you.
Patrick, your mic's muted.
Okay, Pat Bartholow, do you hear me
We read you.
now? Okay, Pat Bartholow in Auburn, California. I've been a member for a number of years of Synergy Moon, and recently joined to help out as I can with Aaron and I'm sorry, with gosh, I can't think. What's your name?
Ethan.
Ethan. Yeah, I want to say Aaron for some reason. Ethan. Okay.
Yes.
And also involved as a sort of a remote advisor to the team
Alpha CubeSat.
Alpha CubeSat.
Yep.
4-year degree in surveying and photogrammetry with a fair amount of aerospace experience due to, for a number of years, where I was at Monterey, they prohibited any new development in Monterey, which pretty much killed the whole surveying industry for a number of years. And it was the drought in '77, so I explored other electronic means or electronic avenues. Went back to school, learned telecom and other skills. But anyway, so we're ready to present my background in aerospace. The closest background is through Moonbounce, through a personal interest and pursuit of Moonbounce communications, specifically Moonbounce used with large dishes, giant dishes such as SRI, such as Jamesburg, such as the Arecibo dish, which is the biggest of them all. And I was fortunate to be able to finagle events that were known pretty much around the world about those dishes under a moniker of Echoes of Apollo. It started with the anniversary of the Apollo moon landing. So we wanted to get something going to celebrate with a Moonbounce event that commemorated the 40th anniversary of the Apollo 11 moon landing. So I'm self-taught large, although I have a 4-year education and more. I'm self-taught in most of the space sciences through Moonbounce and through my own personal efforts. I was involved in the ISEE-3 adventure a year or so ago.
Oh.
Was able to acquire a 700-watt S-band transmitter. Actually, it's L-band and S-band for that effort, which turned out to be a useful or valuable uplink to the ISEE-3 satellite. Most of you probably saw or heard or maybe followed that adventure somewhat closely. I had a really good time with that, and it was about a 6-month effort on my part. So, and that was actually, sorry?
Some of us really followed it closely. I was able to eavesdrop on a lot of what you guys were doing.
Oh, really? Okay.
Yeah, 73 KD0CXH.
Okay, CXH. Okay, AA6EG here.
Excellent.
So I have a sort of a heart and a passion now for space, and I've gotten into a business. Don't have my first client, but I have the tools and both the mental tools and the physical tools to do ultra precision scanning, 3D scanning of large dishes. So if JPL Goldstone needed to find out how many millimeters off their 2 o'clock quarter of their big dish is, I can tell them how many millimeters off that is from a perfect parabola. So we plan to do that as a service business in the space industry.
Oh.
So, okay, where are we? Anybody? Okay, who's next, or who else needs to do introductions?
Oh, everyone's introduced, and the floor
Okay.
is yours for the presentation, Mr. Bartholow.
Okay, let me see if and you guys all see my screen, right?
Please
Not
open your
yet.
window and share screen, please.
Oh, let's see. Oh, okay, wait a minute. Okay, share screen. Screen share. Presentation 1. That's strange. Okay, so let's do CAISPN.
Okay, we have visual.
Okay. I just don't have the specific. Oh, why is that? Let me see here. I might as well. PPT. Where's my PDF? Well, I guess I can run it through PPT.
Yeah, let's run the PPT. We're fine with that.
Okay. It'll load PPT, then I'll do a slideshow from the beginning.
Okay.
It's weird why this thing crashed right at the instant of beginning the last time.
Document is recovering because it was open while it crashed. That's why it's trying to do the recover there.
Right.
Yeah.
And
I
it'll go
recommend
through another.
click the upper one under original, and that ought to get your recovery.
Oh, really? Original. Where's the original?
Up there, see available files. Top one. Click on that original.
Okay, I bet. Oh, okay, right.
Actually, hold on that. Excuse me. Click on the one on the bottom.
It's gonna come up. Oh, wait a minute. Why didn't that go down? Okay, let's see.
Patrick, do you read me?
Yes, I read you.
Oh, click on the one on the. Oh, actually, excuse me.
Okay, here we go.
All right.
Here we go.
Okay,
now,
you're online.
Now let me say slideshow from the beginning. Come on, slideshow. Why doesn't it give me a prompt from beginning? Normally when I say slideshow, it asks if from beginning, and I just click from beginning and it starts. Right now, it's not starting for some reason. Let's see.
Shall we switch over to the PDF?
Let's see if we can do that.
Okay, standing by. Okay. I have a backup PDF here on my desktop if we need to present off my screen.
Let's do that. Let's see how that works.
Switch to screen. Okay.
Let's see. So I should stop screen sharing, I guess, for me.
Yep, terminate screen share. Flop and let's turn over to presentation. Start screen share. Okay. You have my screen. All right, so page 1. Go ahead, Mr. Bartholow. Tell me when to flip.
Okay. I don't. Oh, okay. I got it now. Gee. Hold on a second. Let me expand that. Ooh. Okay. I'm losing the bottom bunch of screen space. Let me see if I can move this up. Okay. Wow. Strange. My image is being encroached upon by our individual pictures on the bottom.
Oh, don't worry. That's okay. That's just an artifact of the presentation, but everyone can still see. Okay. Yeah.
Okay. Okay. In any event, so I named it Moonbounce as a segue, as a pathway to large dish operations in and at spaceports. And I'm not an expert at all in spaceports. I'm a logical person, and I have a background in marketing and a whole lot of things that relate to spaceports. But it made sense to me that a communications site is a needed asset for a spaceport, just like all the other things that make a spaceport successful, like restaurants, recreational facilities, technical parks, research parks. All of those kinds of things go together to make a spaceport successful and somewhat smooth in an economic sense. If it was only launching and launching missions and rockets, it might have a rocky road to stay open throughout the year. So there's a map that I just picked off the internet that showed many of the spaceports that are currently either operational or planned. And so I'm going to emphasize Moonbounce and show you 3 of the major Project Moonbounce systems that I had a hand in, and the program that I had a hand in developing. So let's see if we click to the next slide.
Okay. Next slide over.
Oh, okay. There we go. This is the first big dish operation that I had a chance to have a hand in. Jamesburg Earth Station is down in the Monterey area, about an hour and a half from the city of Monterey, in the wilderness, sort of. Actually, it's gorgeous, God's country. When it was shut down in the early 2000s, and then there was an announcement in the local paper when I was down there that somebody bought it. And so I said, whoa, somebody bought it. What's he going to do with that? And so I contacted the guy and said, hey, what are your plans? You know, he said, I don't know. It'll be, we're probably going to scrap it. We just got a $250,000 estimate to scrap it. I said, oh, don't do that. Please don't do that. I could find a use for it. And so that started a long negotiation and then marketing and advertising program led by me to put Jamesburg to use. And in the process, we said, well, why don't we do Moonbounce with it, because that's what I want to do anyway, and that'll sort of shake down the whole system, the dish, the feeds, the drives, the computers, all of those things will be given a pretty good workout for Moonbounce. And he says, oh, okay. And his angle always, well, what's in it for me? You know, I don't know if I want 50 of you guys climbing over my antenna and all this, and who knows what's going to happen bad in that process. We said no. We all signed and gave him hold harnesses and had a really good time, which for me began in 2005. And by 2007, we had, actually 2006, we had built the Moonbounce station in and around that dish, and we're going with really, really, really powerful Moonbounce signals off the moon. So that's that. The building that's adjacent to that was a Cold War era 2-foot thick concrete walls, believe it or not. 2-foot thick concrete walls, a 1-foot thick concrete ceiling, and 20,000 square feet. It was sort of a Cold War era philosophy.
Wow.
Okay. Okay, next slide.
All right. Oh.
Okay. Even this picture cannot give a proper feel for the giganticness of a 100-foot dish. That's me climbing a ladder. It's non-OSHA. Somebody pointed out to me, hey, that's not cool for OSHA. I said, you're right. I'm a volunteer at that time, and once we got into a commercial situation, that ladder would have to be improved with lanyards and harnesses and safety devices that didn't exist at that time. But that's just me climbing up to the hatch to get up to the feed point of the dish while it's in the bird bath position. So, okay, and right there at that point, the bottom of the ladder is about 70 feet above the ground. So right where my arrow is about 70 feet above the ground. I'm about maybe 80 above the ground. Okay, next slide.
Oh.
I was able to. There's a whole side story. If we have time, I can tell you about it. We had to image the dish and find out if the actual dish, the actual physical shape and location of the surface where, you know, all over the dish was correct according to the mathematical parabola. Well, it was actually a shaped dish. And so it was a hard time for me to find the guy who did the actual dish design. He was getting older, and he said, oh, I have a big file full of Hollerith cards that he programmed in Fortran to compute the optics of the dish. And he says, if I can find those and convert those to CD-ROMs and then run it again, I can print you a precision dimensions of the whole dish. This is a Cassegrain dish. Everybody probably recognizes that. This mirror here is a Cassegrain mirror. It's a hyperbola. This is a parabola, but it's been warped a little bit, shaped a little bit. Because this point here is the phase center of the dish, a point source at that location, and with that Cassegrain dish will properly illuminate the whole dish. So critical part is where is that phase center, and how wide is this angle? So the feed that you develop, whatever band you're on, has to develop a beam pattern that doesn't splay over too much off the edges of that mirror. If the beam pattern was like 11 times 2 is 22, if the beam pattern was 30 degrees, you'd be wasting a lot of energy that would not be used by the mirror.
You're saying the point
dish
source is down here within the dish off the 61-foot mark and broadcasts upwards and then sideways and out.
Yeah, you'll see the actual physical horn that we created. We fabricated from scratch a horn, because the original horn, this was a C-band dish. It was 6 gigahertz. So we were going on 1.2 gigs. So that's a trick. That's a real challenge with any kind of a new dish that's given to you or that you have access to. You have to figure out how to mount and design a feed horn that's going to properly illuminate that mirror. Or if it's a prime focus dish, like if the feed was actually up here, you have to illuminate the whole dish, like so. And that's tougher because that's a much broader angle to cover the whole dish. Okay, so I was fortunate and lucky to get this because the guy had it was a PDP-8 or something, some ancient computer that he used to generate that. It's really really crazy. Some history. Okay, so are we clicking? Are we able to advance in the slide?
Okay, advancing.
Yeah. And that's so you saw the engineering diagram. This is the reality of it. This is about 10 feet in diameter. From edge to edge, it's about 10 feet. And this guy is the original C-band horn. And I was told that horn and associated feeds, there's 4 corner feeds around the corners of that, would back in those days was like $250,000. I mean, it's insanely expensive. We built ours for about $200.
Wow.
And they didn't believe us, actually. So they said, you're going to use a $200 feed horn that you built yourself from sheet metal and stuff? I said, yep. And, well, ours cost $250,000. But that's how the government and General Dynamics and those guys kind of work. Okay, let's go to the next slide.
Next slide.
Okay, literally, this is the feed horn that was built. Actually, we adopted. It was already built. This is Jim Moss, N9JIM, one of the key people that I brought into the team to work with the team to build he had the EME equipment and the know-how to build a horn and all of that. It turned out we had very little time to really design a proper horn, and if we did a backwards analysis, this part of the horn, this flare at the frequency that we wanted in order to illuminate that Cassegrain mirror properly would really have to be about 4 or 5 feet long. So it was not an optimum. But anyway, it was an experience, and literally nuts and bolts and wrenches and wire cutters and soldering irons literally on the top of that 100-foot dish that we were standing on. Next slide.
All right, next slide.
And that's the dish installed, dropped right down the throat of the original C-band dish, and aligned as close as we could to collinear with the C-band dish. And of course, it's pointing up to illuminate the Cassegrain mirror that's above it. Next slide.
Oh.
There we go. And now we're looking down the throat of that same feed horn, and you can see literally C-clamps and tin snips and aluminum. And some of my guys that are professionals sort of just say, "Whoa!" And I said, "Hey, it works." and we have systematic ways to align it and calibrate it and all of that stuff. So they said, you know, this dish, this part of the horn originally for the thing literally probably cost the better part of $250,000 because there was. Sorry.
Oh, go ahead. Go ahead.
Because you know, they made 5 of them in the world. Of this design dish. Yeah. So, and plus it was General Dynamics and it was a government job, so why not charge $250,000? Okay.
I'm reminded here of my Mojave days in being taught there's the $1,000 solution, the $10 solution, and the 10-cent solution, but which one do you want right now? And I just remember the guy would, you know, I'd say, hey, can we weld this together? And he hands me a C-clamp and says, have fun. And I'm like, okay. You know?
Right.
And then just clamp it together and we'll be all right.
Right. Yeah. So it turned out that this dish, this feed, as inefficient as it was, I said this would really have to be 4 or 5 foot long aluminum cone there to be properly illuminating the Cassegrain mirror. Next slide.
All right, next slide.
By the way, okay, there's another. This horn is fitting inside the other horn, and its position along the center line, the co-center line on both horns, up and down, is rather critical. The phase center of these kinds of horns is usually a few inches outside the rim of the original horn. So you see this is the rim. So, and we don't know, it's sort of empirically determined, but the phase center that you gotta meet, that you gotta put your phase center on its phase center in order to efficiently illuminate the dish. So we got lucky and were able to position our feed in and out of the mouth of that horn fairly close to the phase center. So the phase center is something whenever you're going to play with a dish or modify or work with a dish, you've got to know where the phase center is and then hopefully make your feed match its position in the phase center. Not only that, but this has to be pointed pretty closely to the center line of the Cassegrain mirror. Next slide.
All right, next slide. Oh, yes.
Okay. Live via Moonbounce, Echoes of Apollo. That's something that I coined as our event, Echoes of Apollo, because it was Moonbounce Echoes as part of the Apollo 11 not memorial, anniversary, and so we called it, and that worked, and we've done several Echoes of Apollo events. Well, we lost our slide.
Excuse me.
And now we're getting to something we might be able to get lucky with now. If not, we can resolve it by giving you a link directly to the audio file. But if you click on that speaker button, we will hear a two-way conversation with William Anders, Apollo 8 astronaut, who took this picture. He joined us in celebration of Echoes of Apollo and gave an a talk about his impressions of making that picture. And everything you hear is off the moon, is via Moonbounce. So, Ethan, I'm not sure if this will work, but click on that speaker.
Actually, when I click on the PDF, it advances to the next slide, unfortunately. We'll have to show the link afterwards.
We can do that. Discussion. We can do that because it was a very, very powerful and one of the best EME voice bounces that I've heard, and it was we were interacting live. Myself and Lisa Sonne, S-O-N-N-E, who's a writer for Wired magazine, conducted about a 3-minute interview off the moon with William Anders of Apollo 8.
I must admit there's a little irony to the name there, because son is French for, as I understand, for sound.
Really? Okay.
Yeah.
Okay, I thought it was sun. I was S-O-N-N-E. I thought it might be sun.
It's German for sun. It's French for sound.
Oh, okay.
More specifically, the sound of a bell making a tone.
Okay.
Yeah.
Okay. Next slide, then.
All right. Let's see. Oh, this is the interview. All right.
and I don't know if that's going to work, but let's wait till afterwards,
Okay,
and
sounds good.
play that, and we can just give you guys a link, and it's a mind-blowing chat. I mean, to hear Apollo 8 astronaut William Anders off the moon, almost crystal clear, is amazing.
All right.
Okay, next slide.
Hmm.
This is the stack of control computers that control the Jamesburg dish. That's sort of the human interface. You can program that dish to track almost anything with that keypad or the buttons and so on. Large amounts of the computer go to self-checking for safety. You're swinging, I don't know, 150 tons of steel with monster gears, and if the computers don't check for various safety conditions, you could have very expensive and even dangerous problems with a dish. So a large part of the computer is the logic and the safety checks that it goes through or monitors completely while you're moving it. And we got introduced to that, and it was really scary for us because the dish had not been used for about 5 years. And while we were learning on the dish and getting it to the point where we could move it, we were at some stage where we said, all right, if everything works and all the sensors are right, we should be able to move this dish. And everybody said, well, okay, are we ready? Are you ready for that? Suppose we can't stop it. Do we have a emergency stop button? All those kinds of things, because it was scary. I mean, the size of the dish, when you're standing underneath it, all this is directly dead center underneath the dish itself in the turret holding it up. Yeah. So it was kind of a scary moment to first turn the dish, kind of like what a test pilot would do when he took like a brand new prototype airplane, took it off for the first time. Yeah. That's probably a very scary moment.
You guys were standing right underneath this, and the risk is basically if you guys move it the wrong way, this dish comes through the ceiling right on top of you guys.
No, it's not likely that way, but not likely to do the turret and the tower were like bulletproof. They were steel, and it was like 3/4 inch steel surrounding the bearings and the pivots for the dish. So it's monster. Some other time I can show you other pictures of the steel plate that. I mean, it's just really massive. A tank. When we're up around the dish, around the support structure, it looked kind of like a tank rather than, a delicate dish. So okay, that's what we dealt with. So next slide, please.
All right, Jamesburg tracking display.
Okay, it had a nice video display with precision, azimuth, and elevation readouts. Told you where the current dish was. It had very precise encoders that did that. And you see manual rate control unit. We had a handheld box that normally you would have software that would be controlling the dish just to move it around, and it was pretty much or I should say firmware, pretty much hardwired firmware that you got the dish to do what you wanted it to do. In our case, we wanted to manually move it anywhere we wanted to, and we had a manual control box to do that. Okay, next slide. So that was down to 1/100 of a degree, which would be 1/100 of a degree is about 6 minutes of arc. So we took our laptops, which had canned ham radio Moonbounce tracking programs, and commanded the dish via a serial port to its computer. Basically, we updated its position as frequently as we decided we needed to do. The moon doesn't move but about 1 degree every 4 minutes. So it's not like a satellite. It doesn't need corrections that often. But we had laptops with standard programs, standard off-the-shelf ham programs to track the moon, and they interfaced fairly easy, not perfectly easy, but fairly easy to the computer, the Vertex computer. Next slide. This is the power center. The 4 boxes on the left cabinet are, what do they call them? Variable frequency drives for motors. They produce square waves that control the power applied to the azimuth motors and the elevation motors, and we're talking 25 horsepower motors here. They're pretty beefy, driving some really beefy gears.
Mm-hmm.
So they also have acceleration, deceleration curves. So when you want to stop the dish, it doesn't just stop, because there would be shock loads on the whole drivetrain.
Mm-hmm.
So there's a fair amount of computing, and then in the right cabinet, that little let's see, you can see my cursor, right?
Actually, I'm controlling the cursor right now.
Okay, I've got it. Oh, okay, that's your. Okay.
Yeah, this is mine.
Okay, but do you see this one over here on the right?
No, I actually
okay.
can see my screen right now.
Okay, so
Yeah.
the aluminum box with a blackish center is like a red light, green light. Right there.
Yeah.
It's like a red light, green light condition, kind of like somebody told me submarines are kind of like that.
Mm-hmm.
Hatch conditions, open, close, safe or not.
Mm-hmm.
And if all lights are green, you're good. If you see any red lights, there'll be also beepers. And you said you better investigate that, because something is not right in the sensing system. Usually it's a sensor. It's not that the dish is wrong, but it's the sensor that's wrong. Okay, so we had to figure all that out, and that was scary, because we were messing with the control system, and if we didn't want to go over, we didn't want to go beyond the stop, so to speak, on the vertical or horizontal motion. So it was scary, and we proceeded very cautiously and asked questions about what could happen if all that. Next slide.
All right, next slide. Interesting.
Okay, now we're leaving Jamesburg for the time being, and I want to show you Landsat, which I investigated. Landsat has satellites that monitor and watch Earth-related phenomena, temperatures and waves and a gazillion different things about the Earth. So they have a whole constellation of satellites that are looking back down at the Earth, can send images, infrared, whatever frequency band you want. And this is the ground station network that they have. It's pretty comprehensive.
Mm-hmm.
And most I have the specs on each of the ground stations, how big the dish is, who runs it, what frequencies they can handle, all those kinds of things. So this kind of stuff can be very useful for mission planning if any of these stations, and they are, willing to collaborate or support let's say a CubeSat mission. So if you talk to them nicely and they don't have other things to do at that time that you need them, it's theoretically possible to collaborate with these guys and create your own ground station using these ground stations for Landsat.
Patrick, I kind of have a question for you later
Sure.
that I asked the Planet Labs people earlier.
Okay.
Regarding purchasing time on a ground station, but I'd like to save that for the business application discussion afterwards.
Sure. We'd be glad to talk about that.
All right.
Next slide.
All right.
Now, this is in Mexico, near Cancun, by the way. If we ever had a duty to go down there and either service or operate or calibrate or get online that station, it would be a pretty nice assignment for anybody that was on a payroll, especially if you're on a payroll, because while you're off, you could have a hotel in Cancun.
Mm-hmm.
And this is a critical Chetumal Landsat station that was abandoned a few years ago, budget cuts and such. And they had a staff of very capable Mexican engineers that were just all out of work. I contacted them, talked to them, and found out about the history of that. That's a 8-meter dish, and it's at the top of a dedicated building for that ground station. And it's surrounded by kind of jungle-like material. I have another photograph that shows all those trees totally stripped of leaves. They were just looked like a forest fire had burned them, and that was the result of a hurricane that blasted through there and just ripped off all the leaves off the trees. And it also did damage to the dish. It didn't come off or wasn't catastrophic, but it's out of spec. And in fact, right now the dish is being refurbished. Okay, next slide.
All right.
This is that station. This is the block diagram of the station. Has 3 bands: X, an L and S band. So it's quite a versatile uplink and downlink station, and could be and this is typical. This is a typical station, not a carbon copy necessarily, but a typical Landsat station. So if being X and L and S, you could do deep space stuff. You could do L band, S band. That's the lower microwave bands for any of your CubeSat requirements. And that's just a block diagram of the station, connection to the internet, remote controllable. I have not operated the station, but I've seen this diagram. I had to work at getting these diagrams. So let's go to the next slide.
Oh, real quick question
Sure.
here, because I see that interface between LAN and WAN. Does that mean that this station could relay internet signals, or is this LAN WAN
Yes.
intended more for? Oh, okay.
No, the WAN is the internet. In most cases, I guess it doesn't necessarily have to be the internet, but in this case, it is the internet, so you could remote control the station.
So you can use this for both remote control and broadcasting internet access up to satellite access.
Yeah.
Oh,
yeah.
brilliant.
Let me think about that. Yes, I think so. I'm pretty sure it can.
Oh, brilliant. All right.
So, and I would say most also this station is probably somewhere between $2 and $3 million station. So that's what you're looking at if you wanted to create one of these. It's about $2 or $3 million from scratch to build one of these, and that's only an 8-meter dish. It's not a 100-foot dish.
I'm assuming when you say that price, you're talking about literally the turnkey price, that $3 million, and you have a complete working asset.
If your CubeSat team is, if we need to build and have the money to build a dish like this, 8 meters and X3 bands, you're looking at $2 million or more. Okay. Next slide, please.
Next slide.
Plus the building, and security, and all of those things that you need to keep it operating. This is the top floor. The racks full of gear that are part of that $2 million that run the whole station. And I haven't been there, and I haven't seen a breakdown of exactly what all these panels are. But from the block diagram, if you compared the block diagram to this, you could probably figure out what the modules are. So, but that's what a Landsat ground station cabinetry inside looks like. Okay, next slide. Let's see, how are we doing here? About 5:30. Okay. Next chapter of the story. We got permission to do Moonbounce from the SRI dish. It's a very, very, very famous dish in above Stanford, and it's owned and managed by SRI, not Stanford. That's actually there's sort of a political sensitivity there. SRI and Stanford are different entities now. And they do related things, but they're in a business sense they're not the same. And SRI is very how would I say, sensitive about this is an SRI dish, not a Stanford dish. All the locals know of it as the big blue dish up at Stanford. So we stopped in there when we were coordinating our planning for Moonbounce, using probably one of the biggest dishes in North America. Next slide, please. It's on Ravenswood. Okay. Moonbounce Communication for Science, Space Science and Education Outreach. My angle and my wedge to get in the door and financing is STEM education, and people pay attention to that. And why should spaceport developers consider a large dish Moonbounce education and recreation program? First of all, Moonbounce is fun. If you can get kids and high school and college kids doing Moonbounce and hearing their own voices coming back off the moon, there's a big wow factor there, a really big wow factor. And if you're creating a new station, it's not easy. It's like diagnosing a huge software program. It's not going to work the first time or the second time or the 10th time. You're just going to have to debug and debug and debug and get it to work. And it's very difficult to get a Moonbounce station to work even after you've assembled it and have first light, as they say. But Moonbounce teaches or demands mastery of many or most space science communications disciplines: orbit determination, tracking, path loss, patterns of antennas, internet interfaces, all of these things you're going to have to learn, or at least get an operational knowledge of, in Moonbounce. But it's fun. When you do it and you're successful, it's really fun.
It's also
Sorry?
fairly forgiving because, as you stated, it only moves a degree every couple minutes. It's not
Yeah.
like trying to catch a satellite via LEO.
Right. That's right. That's right.
Yeah.
And so I've been promoting, and I've submitted a professional paper in Mexico at one of their space conferences, pushing the fact that Moonbounce is far less expensive than a CubeSat program, and maybe even by a 10-to-1 ratio or better.
Oh.
A high-quality, single sideband capable Moonbounce station component inventory cost about, actual cost to buy the pieces, $25,000, with all purchased new equipment. Now, if you had a SRI dish or a Landsat dish or some other dish that was given to you, that's $5 million to $20 million. So, but those are around. You can find these big dishes from time to time. So, with $25,000, and if you're labor, if you have to pay labor, we did it volunteer, but you can only do that for so long.
Yeah.
I'd say $100,000, $75,000 of labor would put 2 or 3 guys 6 months worth of work to commission a station once you got all the pieces in front of you.
Mm.
Okay, so I'm figuring, just a round figure, if some university hired me and said, Pat, come over, bring a team of guys, buy all the gear, we got this dish in the Outback we haven't used the last 10 years, make a Moonbounce dish out of it, probably the contract price would be something like $100,000. Now remember, once you get that dish for $100,000, you've got a dish that's going to last 10 or 15 years. It's got some maintenance costs, but you got an operational ground station that'll do CubeSats or Moonbounce or deep space if it's a big dish, for $100,000 investment. And if you look at the history of CubeSat, most CubeSats missions, if you look at them statistically, were less than 2 months. And a lot of times the design life was even 2 weeks. So a lot of universities and military and all the people that have shot CubeSats off, once they're launched, many of them are done in 2 months. Fewer are done in 6 months, and there's a few out there that have lasted, a few years, or maybe quite a few years. So, to me, that you spend $100,000 for 2 months worth of prime time with your satellite in orbit, as opposed to $100,000 gets you a ground station that can generate revenue, that can handle other people's satellites for download, uplinks, and downlinks, that can do Moonbounce education. It's quite a versatile capital asset that I think is far more valuable for the money, for the dollars, than 2 weeks of orbital activity with a CubeSat. They don't cross over completely, and there's places for CubeSats for sure, but I think if you're strapped for money, and you have a dish, spend $100,000 to make a world killer Moonbounce station, and then charge rates to CubeSat missions for downlinking. Somebody says, hey, we got a flyover next Wednesday from 3:30 till 3:45. Can you get the download of the data from our mission? I said, sure. Start your credit account with us, and it'll cost you $400 for, I think, up to a 15-minute download. I've heard numbers kind of like that. That's on the low end, I'm afraid. That's not a monster dish, but that's a ground station. Fees, $400 for 15 minutes worth of download.
Yeah.
Okay. But if you could book a whole bunch of stations, and especially if you could automate that with all the CubeSat players that there are, you could have many downloads per week, and generate $400 receipts as frequently as you try.
Hmm.
Okay. Okay, next slide.
Next slide.
Okay, that's the Stanford dish that we used. It's a beauty, and they repainted it all. When we had it, it was a lot of rust stains and stuff on it, and it worked fine, but there was a lot of rust. So, and the expense of maintenance of I mean, just painting that, you can imagine, just painting that, especially if you had to do corrosion control, would not be cheap. I'd bet that you could spend $100,000 easily just painting it and covering up the rust spots and making sure it's safe. That dish is historically very important. It was the first dish that the CIA created, not for quote-unquote astrophysics research, but for other covert programs that are now historically documented. And you can look up CIA and Moonbounce and find out what they used it for. But they basically watched and characterized Russian radar, missile radar, for the signals when they bounced off the moon, because they were strong enough for a dish like this to pick up the pulse repetition rate and the frequency and all of that stuff of a radar. And they discovered that, and of course they didn't tell the Russians, and were eavesdropping a lot on the Russians for a long time. The Russians had no idea. And one of the ways they did this, they figured out the geometry. They said, put that dish low to the horizon, and put the moon low to the horizon from the Russian border, and then play chicken as they used to do. Fly American jets from, let's say, Japan at Mach 1 or Mach 2 right at the border at some place that they want the Russians to illuminate their radars. And when they did, the radars happened to be painting the jets that were provoking them, but it was also bouncing off the moon and back to Earth at this dish. So they got very clear, clean signals from the moon, and were able to characterize the frequencies and all the necessary characteristics of the radar from the Russian border not air traffic control. What is it? The Russian missile control radar. So that was the origins and money and all of that for that dish. It's very historical. Next slide.
All right.
And on that dish, on our Moonbounce game, that's the feed that we were able to get actually off the shelf from SRI, because it suited us. We were at 1296, 23 centimeters. 1296, it turned out that dish would work, and we built a hybrid, what they call a hybrid feed on that, which caused circular polarization. You guys may or may not know all about that, but circular has a lot of advantages because polarization at some frequencies and some conditions is somewhat random, and if you're linear polarization, you want to match your linear polarization orientation to that of the incoming signal. With circular polarization, you don't care. You just have to be, whether it's right hand or left hand circular, you have to match that. But other than that, the angles don't matter. So, but it's more complex. It's a kind of a complicated feed to get that to be circular polarized. Next slide.
Mm-hmm.
Oh, by the way, don't go to the next slide yet. Stanford has a really nice, convenient feed point there at the prime focus. This is not a Cassegrain, by the way. This is prime focus. The cabinet that I'm standing on has all the electronics, the feeds and the transmitters and all of that. And this whole thing is sitting now right on the ground. The bottom corner of it, which you can't see, is just about touching the ground, because they can, with a remote control, lower it from its high up in the air, difficult to work at location to the ground. So servicing and adapting and troubleshooting can be done largely right at the ground, which is a huge convenience and cost effectiveness factor. Okay, next slide.
Did they let you take a hayride?
Let's see. Actually, I've got respect. By the way, I'm a skydiver, so the heights didn't used to bother me. But I jumped for over 1,000 jumps from 15,000 feet. But heights in and around dishes, I wouldn't say they bother me, but I'm very mature and extremely cautious. I'm not casual or comfortable because a 20-foot 50% of falls to the ground from 20 feet are fatal.
Yep.
20-foot fall. That's
Yep.
all it takes. So anyway, you can see a bracket and some terminal blocks of the devices we had to mount to that Stanford horn. One was a relay, one was a low noise amplifier, a couple of hybrid feed, and all those interconnects. We built that part. So anybody that wants to borrow or adapt a dish that's given to them will have to figure out the feed. They'll have to either design that whole feed itself out of sheet metal, or borrow one, or get one that's already made, and then it's really not that difficult, bolting all these relays together and making it all work. That's the fun part of it, because you learn a heck of a lot. Next slide, please. That's just a slight distance shot of the dish, an approach shot. That big building is sort of a parts and labs and stuff like that to service the dish. Next slide. That's the back side of the dish. You got some heavy runs of coax, and most big dishes have to have some sort of a rotating joint for their hardline, and that's not trivial nor cheap. So if you inherited a dish, for example, and said, hey, we'll give you that 50-foot dish or 100-foot dish, it's yours, and they say, oh, by the way, the joint needs replacing, you say, you know, maybe that, I don't know, maybe that's $25,000 for just that part. So be careful what you ask for, and everything that deals with these things is insanely expensive. So hopefully you get one that's in really good shape. Next slide, please.
Patrick, real quick side question. This dish somewhat resembles the dish Magneto was moving in X-Men First Class. Was this the dish, or was that somewhere else?
Don't know X-Men First Class. That's a movie? I assume that's a movie.
Yeah, that's a movie.
I wouldn't be surprised, though. I'm sure the dish is open to bookings for any kind of movie, you know, at a fee, just like Arecibo was. Arecibo was open for what was the not Moonraker? It was
Eagle Eye.
Yeah. Okay. Next slide.
Yep.
Let's see. Do we have a tight end of the hour kind of time limit on this?
Well, we can go until 8 o'clock.
Okay.
You start at.
Okay.
Yeah, you got like 18 minutes.
Oh, well, that's what I'm saying. So, okay. So This is the director of the dish, Dr. Cousins, and this is the control room for the dish. All the meters and the status monitoring of the dish happen from right there. And this room is on the platform of the dish. So wherever the dish rotates in azimuth, this room rotates in azimuth. So you're floating on the dish structure.
Yeah, because that little house underneath the under the cradle, this little house right here.
That's right.
Gotcha.
Yeah, that's it. Next slide. And once we got the Moonbounce station working, we had an operator's position with some ham radio gear, and that was our operating position at which we did the Moonbounce operations. And I wrote an article in CQ magazine. Actually, wrote a series of them, and they thought enough of them that they had a what do they call it? Diorama? I think that's the name for it. This, I was amazed. I was flabbergasted because it's a work of art, literally a handmade work of art by a really good guy. If any of you guys do space stuff and you need to award somebody with a really classy award, I can highly recommend this guy and this concept. He used wood and plastic, and he recreated a photograph. That photograph of the dish in New Zealand is a very good, and it's three-dimensional. It protrudes from the flat board.
This is that little bas relief right here I'm circling behind this gentleman's head. Is that correct?
Yeah.
Oh, okay. Excellent.
So it's very much a 3D thing, and the guy that I have the master photograph of that dish, and he did an incredible job of making that into a 3D. I'm guessing, I'm only guessing, but I'm guessing that's somewhere between $500 and $1,000 to make that. And CQ gave it to me for the magazine for writing the articles. Okay, next slide.
Mm-hmm.
Okay, slightly before that of actual operation, we were assembling the station.
Mm-hmm.
This is Mike Stahl on the left with a hat. Very, very famous. He's the owner, founder of M Squared Antennas, one of the biggest, USA-based antenna makers of all kinds of stuff. And trying to think of the gentleman's name on the striped shirt, and I can't remember his name, nor can I remember the gentleman that came out from L.A., the guy with a yellow shirt. But we spent 4 hours putting it all together and testing it, assembling it all, checking it, and getting it to work before we actually got on the air.
Mm.
Okay, and then behind all of this, you can see a patch panel, the copper on that aluminum frame in the back. Those are all very high power, thick coaxial cables that run various programs, including military programs. And you can see above the yellow shirt guy, above his head, that black stripe that's sort of in the shadows back there, that's also coax, probably 8 inches to a foot diameter. It's big stuff. And when you're running millions, megawatts, you need big coax like that.
Mm.
Okay, next slide. We'll start hastening up the slides. Okay,
Right.
so that's more operations.
Mm-hmm.
Next slide.
All right.
More building. The rack in the blue steel rack with a bunch of panels on the front is most of the EME transmitter equipment, and you got a power supply that's sitting on the top. This meter that the guy has is a commonly known. Anything radio has to be connected to a meter that measures standing wave ratio, which tells you if everything's hooked up right, whether you got the right antenna and the coax is all right. And there's at every stage, every joint in the coax is a potential problem area, and will be a certain percentage of them will be problematic when you first set it up. Next slide. But this is the fun. This is setting this up for a bunch of guys, a bunch of friends, is lifetime memorable experiences. Okay, this is Dwingelo. This is an 80-meter dish. No, I mean a 25-meter dish, 80 feet. In Holland, there's a whole long story behind that. It's taken over by hams. It's a historical landmark. It was the very first dish of its size in the world, about 1956, when it was created. And they restored it and got a donation from the Holland government of over $1 million to completely restore it. Otherwise, it would have been scrapped. Next slide. Of course, you see the moon sort of through the mesh surface of that.
Yeah. So that's when they're pointing.
Okay. What's that?
That's when they're pointing it straight at
Say
me
again?
for operations.
Yeah. If everything's right, you. And if you just like the sun, actually, what they do is they test pointing by pointing at the sun at the prescribed azimuth and elevation. And if it's daytime and you can see the sun, it'll cast a shadow point straight down dead center into the base of the dish of the antenna, and that'll clue you into that your optics is right and your tracking system is right. Okay, next slide.
Okay.
By the way, that Dwingelo dish, you see that same building underneath the dish there that floats and moves with the building. Yeah. The biggest dish on the planet that I was able to convince, and through Cornell University, to do a Moonbounce in 2010. That's an aerial shot, standard off from the air shot, classic one of the Arecibo Observatory. 305-meter diameter. It's 450 feet from the base, where you see the shadows on the base, to the bottom of that cave, that geodesic dome-like device, about 450 feet. I was able to go up there. Actually, we had to go up there to do work on the getting the antennas working. It was another lifetime experience. If anybody gets to go to Arecibo or might on vacation or otherwise, and you would like to see an insider's tour, not just a tourist tour, but an insider's tour, I can arrange it with the people that I know there.
Oh, brilliant.
Might take you up on that.
Me too.
Did we lose him?
Uh-oh. Let's see. Eric's here, Patrick's here. Still have them. Ah. Interesting. Oh, yes. Okay. Hello, Patrick. We have you. Patrick, how do you hear?
Ethan, this is Eric.
Yeah, what's up?
I don't know what the schedule is, but I don't know if there's going to be an opportunity for us to have some discussion following. So I don't know how long will the presentation supposed to last.
Schedule was set for 6:45 Central to 7 approximately 7:45 to 8:45 p.m. And then the whole segment was going to last 2 hours. So last hour was going to be for discussion. So when we hit 8 o'clock to 8:45 p.m. Central is when we have the panel.
Great, sounds good.
Okay.
Okay, he's having problems.
Okay.
Patrick
has come offline.
Yep.
All right. Kind of a little filler here while waiting for Mr. Bartholow to. Let me put a little invitation in to see if I can port him back in. All right.
Reminds me of a communication that went between the tower and the Apollo 1 prototype.
Yeah.
How are we going to communicate all the way to the moon when we can't communicate to the building next door? Of course, that was actually moments before the Apollo 1 fire, so that does not bode well.
There's let's see. I kind of wanted to. While Patrick was there, I wanted to ask him 2 specific questions related to the biz model of space comms, and he said that you get paid per download.
Are we back?
Oh, hello, Patrick.
We are back.
Yes.
I don't know what happened. It just it was gone. Houston, we have a problem.
All right.
So do we have to restart? Even if we do, I can toggle right through to the right.
Oh no, we're okay. We just need to be able to wrap up the presentation in the next 8 minutes, and then transition to the panel discussion here.
Okay, so I don't have a slide on my screen. Do you guys still have slides on your screen?
Let me turn my slide back on.
Okay.
Screen share.
So we'll have to hustle through this.
Okay, screen share on. All right, there we go.
Okay, there's Arecibo. Next slide.
Okay.
There's the entrance to Arecibo. I did an entry shot, security and etc. Next slide.
Yeah.
There's my house. I stayed 4 days inside this house, which was almost a luxury suite for a family. It was just super nice, and the environment around it was really nice. This was within sight on this patio, on this little patio here. I could see the dish. It was just incredible. And if these things are available and you're vacationing at Arecibo, maybe I could even help you get a hotel room, a suite there, and it'd be way less. I think it's $60 a day for their scientist rates.
Yeah, I think you've got at least one person interested here.
Yeah. One thing you won't ever find in these is a microwave oven, for sure.
Okay.
But they have direct fiber optic fed internet. I mean, if you want to do really high speed, because scientists sometimes have to download monster files when they're doing their science. Okay, next slide.
All
Called the Jodie Foster Suite because it was featured. That very building that I stayed in was the same one that Jodie Foster and Matt McConaughey had. What do they call it? Prime time had. Anyway, they spent their nights together there in the movie Contact.
Oh right.
Yeah. Okay. Next slide.
Yep.
Okay. This is the group of including me of a number of the people that were essential to the Arecibo effort. The guy in the red shirt is a Nobel scientist, Joe Taylor, pulsars, very, very famous, notable scientist in pulsars. And then there's me, and then one of the guys down below, and then there's Angel, and the American blonde-haired guy right there is Jim Breakall, who's famous. And he has a house right in Puerto Rico because he used to do work at Arecibo a lot, professional work.
Mm-hmm.
And some of the other staff. Okay, and if to me, way behind there, you see that red thing with a yellow stripe on it? That's one of those 1,000,000-watt klystrons. There's a lot of interesting pieces around here. I mean, there's not that many of these kinds of things anywhere. Okay, next slide.
All right, next slide.
Okay. We had a problem. Houston, we have a problem. There was our operating position, and we had a problem. We were not getting anything out. The amplifier just off to the left was kaput, and they said, "Oh gosh, what's going on? What's going on?" So everybody was cracking their heads together. This is literally like, Houston, we have a problem. So everybody stood, put their caps on, trying to figure it out. By the way, see that big ceramic and metal and multiple bolts and all that stuff in the background? That's another one of those multi-million-watt klystrons for the radar.
Patrick lost. Loss of signal. All right. Well, this looks like we're having some technical difficulties. I think at this time we might want to transition over to the discussion. We're coming up here on back up here on 8 o'clock Central. But let's see. All right. But real quick thing I wanted to follow up on was the question of how much, what kind of subscription model can you use if you have a ground station on your facility, and you can get so many subscribers, customers, or whatever. What kind of subscription model can you charge? Can you do it the way the telecom and the cell phone companies do, where they say you charge per data rate, per month, or per minute? And is that a typical option that they do for satcoms? If I have a satellite in orbit, can I call up a ground station and say, I'd like to purchase 500 minutes of connection time from your station when I'm in range? And would they do that? When I asked Planet Labs about that, they basically said that it's not for sale on those conditions to use their downlink system.
Yeah, one of the questions I was interested in asking was the what would it take to build a dish from the gimbal upward?
Yeah.
You've seen the facility that we have outside of Walsenburg here.
Yeah.
And it's pretty much black sky, both in terms of light pollution as well as RF. My question is, if we were going to build something, what would it take? And mainly because, according to my latest projection, I'm probably going to end up owning that building in about 4 years.
Oh, okay. So you're planning to make your own. You're planning to make your own comm station right there.
Well, something. It's a building similar to what he was describing. The 2-foot thick walls, the 1-foot thick ceilings, the tower itself is built to hold several hundred tons of radio equipment. So it probably wouldn't be too much of a problem to throw a dish on top of it.
Yeah. All right.
Of course, I need to get a structural engineer to have a look at it and see if that's even a possibility. But from the financial aspect, I'd be interested to know what it would take to make it useful and to get some money back in terms of the subscription model that he was talking about.
Yeah, yeah. Eric, you there?
Yep, I'm here.
Yeah. Kind of curiosity from your perspective as essentially a radio provider for satcoms. Do you got what kind of business models have you seen of how do people bill each other for use of station or use of SatLink for communications?
When you talk about this, do you mean particularly for small satellites, or what kind of missions are you talking about?
In general, like if you have a ground station somewhere and I call you up and say, "Hey, Radio Bro, you own the station. Can I purchase a data connection from you?" What's the
Sure.
typical arrangement?
So, from what I see, and I have done some research on this, it looks like it's really a time. How much time does it take, first of all, to prepare for a mission? So, if you're going to rent it one time versus 100 times, well, there's going to be some setup that first time, and then after that, it's just going to be time on the antenna. And there are some commercial rates out there. I mean, I'm looking at some stuff here where online just while we're having this discussion, and I'm seeing anywhere from $14 a minute up to $130 a minute. And I know previously I've seen some stations that operate in the thousands of dollars per pass. So it depends on what the technology is, but there's it looks like it's just really rent per unit time, and certainly you could prioritize it based on maybe mission and risk and maybe affiliation.
Yeah, yeah. Okay, Patrick, we got you back, but I'm sorry we're at 8 o'clock, so we're out of time for the presentation. We've switched over to the
You got a firm or a hard start and stop time on that. Okay.
Oh, well,
If
yeah.
anybody is interested after that one, after the second phase of this call, if anybody's interested, we can phase.
Okay, a little quick prop here for a couple friends of mine. I'd like to give a little prop shout out to Spaceport Los Angeles. They're a space commercial advocacy organization that recently started in the Los Angeles area, run by Miss Monica Jan, who's been a friend and member of the CAISPN network. They are having a launch event 2016, January 14th, at the Cross Campus in Pasadena. Look out for them. And special thanks to them for their support of CAISPN. Let's see. But back to the discussion. Eric, you were saying about charge per minute and per pass.
Certainly.
Yeah.
I think our biggest challenge upcoming is when we're enabling, let's say, small sat missions. You're not trying to talk to one satellite. You may have 20 satellites in a field of view. And in order for that to be, let's say if you have one facility, how can that one facility support multiple missions simultaneously? Well, now you have to look at conflicts. You have to look at your band allocation. There's a lot of stuff going on, but what we're seeing really, and maybe the reason this is so up in the air, is that maybe it isn't figured out, especially for the new high quantity small mission environment of small satellites, and when they get launched up in groups of 5 to 50.
Mm-hmm. Okay. Patrick,
Yeah.
actually, a question for both the panel and for Eric, because you and I discussed this earlier before in regards to secure communications. If you have a spaceport facility with a downlink station and suppose an asset that was doing a specific secret or other state mission, does it require that any data transmitted from that asset have to go to receiving assets or receive signals from transmitting assets that are specifically on state-controlled property, such as a military base or other type of spaceport facility? And is it a violation of ITAR expert control if I'm a U.S. satellite and I transmit information, even if not militarily, commercially, to another nation's ground station, and the data went through their infrastructure, thusly?
I'd say it's entirely possible those things and restrictions that you described could very well be in force, and the guys that monitor or regulate or oversee ITAR are, how would I say, quite vigorous in their prosecution power, and also, how would I say this? Once you get into the ITAR realm, from what I've read, from what I've seen,
Mm-hmm.
um, first of all, you open an account and there's some money exchanged to deal with the professionals in the government that have to work with you. And it's very easy. It's been told to me that it's very easy for you to even accidentally, inadvertently, and ignorantly get into areas or activities that break ITAR rules. And if that's discovered, they're pretty harsh and not very tolerant of your errors just because you didn't know that, or we didn't explain everything to you beforehand. If you're going to play in this sandbox, you're liable for transgressions, even if you didn't know. So it's very scary, from what I understand. Also, Rhonda, our booster person, Rhonda Milleron, knows a lot about this, because once you get into launch vehicles, you're very quickly and comprehensively in ITAR regions. So she's everybody should get to know her, because she's very a gold mine on that, because she's been there, done that, and had the axe over her head in case she makes a misstep. If you misstep, it can cost you dearly.
Certainly. Now, from a small set, or from a mission perspective, before you're launched, there are effectively agreements that let's say that every provider in the U.S., every launch provider, is not going to put up a payload that's not effectively approved. And to be approved, the government has a set of processes that are in place, and you effectively need to plan your mission. So if you have content, and that content may or may not have restriction, regardless, all of your content has a plan for how it gets to the ground. And if you want to bring your data down somewhere else, the way you do that, your encryption scheme, all that kind of stuff, your command and control, everything, that's all already planned and agreed on, and you need to stick to that plan. And the government will work with you to make sure that it's safe and also agreed on, and then you act in line with that. So hopefully, from an operations perspective, the spacecraft developer or operator has done their due diligence before it ever gets in the air and before any rules get broken.
Yeah, a quick plug for, I'm also a member of an open source spaceflight group called Mach 30, and we have a task force to handle export control issues. And I'm a member, but basically much of aerospace, its export control is because a missile looks rather like a rocket and vice versa. It's got to be there. It's part of it's just the nature of the business. But at the same time, there are certain aspects of aerospace, communications being one of them, that has opened up recently through export control reform. Much of aerospace has been reclassified off of ITAR and into the EAR, which is the Export Administration, which is done by Commerce, not by DoD and all the guys that are really, frankly, anal retentive. Compared to what we're used to with State Department, Commerce is a joy to deal with. And most of your aerospace is going to be under your 9A 515 for spacecraft and associated, going down into the 9Bs and 9C. It's fairly easy, and if you basically are basing it off of something that's already been published, the public domain exemption that we would love to use for ITAR, but it's a pain in the butt, is very, very easy to use with Commerce and with the EAR. So give it a look, how the new export controls are there, and chances are you can eliminate a lot of effort.
I think that's a really good point, and Here at Radio Bro, actually, roughly 14 months ago, one of those new pieces of legislation had propagated through Department of Commerce and actually created one of the new things, and we rode that wave. And I think we actually shipped our first mini SATCOM product the day after the new number came out, and that greatly simplified our export process.
Oh yeah. Oh yeah.
And the motivation here is severe. I mean, in a very large manner, the spacecraft industry is international, and the U.S. has gradually been becoming a smaller and smaller participant because of our own regulation. So they've made a very smart move to say, okay, what really isn't, let's say, tactical or needs to be regulated by the Department of State, push it over to the Department of Commerce, and it's making the technologies that are already accessible able to be manufactured in the United States.
Yep. The biggest thing too is that we're doing things, boneheaded. There's no other way to put it. That's PG rated. Our biggest thing was we had equipment which we were using, which was export controlled, but it was made in China.
All about application.
Literally, and we could not take that thing even in its original box and ship it back to China. It was considered re-exporting.
Yep.
And I mean,
What do you
even
do about tech support?
Oh yeah, you couldn't get tech support. You couldn't do an RMA. You couldn't even discuss with them the alternate uses. One of the prime examples of it is this little guy. It's a software-defined radio receiver that originally was designed for TV. Well, funny
one
thing.
of those RTL.
Yeah, it's a little RTL device, and they're wonderful. They're designed for TVB from out in the East. Have absolutely no legitimate use for TV here in this country without monkeying with the software. But it's a software-defined radio, so guess what you do with it? You monkey with the software. That device can tune in down into the VHF range, all the way up into the L band and beyond. We used it for a software-defined receiver with a couple low noise amplifiers and some antenna work. We used it for one of our prototype ground stations. Problem is, if you make a component for spacecraft communications at the time, it was part of ITAR. So all of a sudden, this little device, which we got off of eBay, once we use it for things and it's documented, it became ITAR. State Department has no problem with that. Our State Department was the problem. Commerce Department has no such problem. They're like, hey, cool. And because it's below a certain amount, you fall under de minimis. In other words, if it's below $200, you're fine. I think I paid like $12 for this. Anyway. And also, because it was published online through research, they immediately went over into public domain exemption, and the device, instead of being export controlled under the 9B and 9C 515 series, is instead considered EAR 99, which is not regulated.
Okay. Kind of to bring the to let the audience know, you can pose questions and answers to the panel here through the questions answers app on your YouTube window, so we can be in here to answer anything that you have. But kind of bringing the discussion around back to spaceports, Patrick, I wanted to know a little more about your analytic for how you determined the cost numbers, as well as if you have any numbers to estimate what kind of revenue can a ground station have. and what if you will, what frequencies and what bands are going to be the most commercially valuable to the to do running a commercial ground station on my spaceport or so.
Right. Um, I have limited experience in that, but I've studied Brian. Everybody should write down Brian Klofas, Klofas, and look him up. In fact, he's got his own Klofas.com, and he was involved in our Jamesburg Moonbounce effort, and he's since graduated from Cal Poly and is now a scientist or an engineer with SRI. So he's quite knowledgeable. He's one of the key, I would say he's one of the top key guys in any evolutions of CubeSats development. And his website is very, very thorough with histories. It has every CubeSat launched, every frequency band used, every modulation scheme used, mission definition, all these in a nicely done database that you can scan. Sort of the history of CubeSats. I think there's been about 150 of them launched now. So he's an immense resource. Let me think. There's a dilemma too that I haven't resolved, because the vast majority of CubeSats, being university-based, the vast majority are educational university-based. For licensing and frequency assignment reasons, use amateur radio bands and amateur radio rules and regs to do that. If you go outside the amateur rules and regs, it becomes very difficult and ponderous and expensive to get a frequency assignment outside the amateur radio bands, which presents a dilemma that I don't know the answer to, because one of the very, very strong rules by the FCC about amateur radio communications is there can be no encryption of any kind, or hidden meaning, and they consider encryption hidden meaning. And I don't know how or if that was resolved. That means your encryption of your uplink and downlink, if it's using amateur rules, can't happen. It has to be all in the clear. And yet, I think the space people require that to some degree, and some missions for sure require it. So I don't know how the resolution of that is.
Isn't there a difference in point-to-point versus point-to-multipoint for ham radio?
There are some differences. Let me think about how that affects.
Because your uplink.
Yes. Ham radio cannot broadcast in the classical sense. You can't. Right. Now hear this, everybody in the USA. This is an announcement from so-and-so satellite. You cannot broadcast. You have to be connected and speaking to at least one person that's on the other end. If there are associated listeners, that's okay, but you can't be a broadcast station in amateur radio.
Right. My point was that if you are doing single point to single point communication, and your antenna arrangement or dish is designed for that, if I remember correctly, there is an exemption to the encryption.
Oh, okay.
Yeah.
That could be. I don't have a thorough understanding of all the rules.
I'm trying to remember the. It's not Part 15. It walks off the reservation as far as amateur radio, but if the signal is confined, it's a different story. It's almost as though it was going through coax.
Okay.
The interesting one, though, is that there is a difference between encoding and encryption.
Okay, right.
So if you're using something that is encoded a little differently, it's not encrypted. You just don't have to tell them the encoding algorithm.
Right. As far as I remember on encoding, some forms of encoding have to be sort of in the public domain. If somebody wanted to find out what the encoding scheme is, they have to be able to have access to that. And I think that's because the FAA, the NSA doesn't like encrypted things in general, and amateur radio operators would be, I guess, suspect if they were trying to hide things. So, indeed, encoding, I think, the encoding algorithm has to be available.
Correct.
Mm-hmm.
So there's a little bit more to the story. When's the most recent you guys have been involved in the small satellite frequency allocation? Has it been in the last 5 years or 3 years or 2 years?
Oh, yeah.
Yes.
Okay. In 2012 and 2013, when our satellite launched over here in Huntsville, or built in Huntsville, launched out of Wallops, we rode the wave of amateur radio getting upset that too many CubeSats were on that band. And that forced into a huge debate, and we all got licensed experimental regardless of what we were trying to do, which half of our team got a ham radio license, and we're looking forward to operate our ham radio to our satellite. So we ended up sitting at the same frequency. That's what we were engineered to. But we had an experimental license because we couldn't get past the fact, or there was a nice international issue of should small satellites even be using the amateur bands. And I don't know if they ever got past that, but it certainly was it was certainly demoralizing as a young ham radio operator to be told, no, go do your stuff somewhere else. And about half our team ended up not getting a ham radio license, and that's probably the reason why. And who knows how that'll affect the ham community downstream, because there's a lot of talent who wants to participate.
Indeed.
It just happens to be in a new manner, which seems overwhelming because there's so many people around the world doing it.
Agreed.
I agree.
So,
This is Pat. I'm going to have to take a break. You guys continue on. I'll be back in about 5 minutes. Thanks.
All right.
great.
So, yeah, it's kind of funny. There's a lot of ambiguity of the rules, a lot of different people trying to interpret it different ways. I get the feeling that we are expanding into an area that the regulations were not designed to address.
Certainly, and that's all. I don't know if that's a good or a bad thing. Creativity comes when there's opportunity. So when people got creative with their small satellites, well, at least from a licensing perspective, as far as should they be amateur or not, people locked up. But experimental accommodated that creativity in our case.
Yep.
We were G3RUH encoded. Any ham station around the world could have that has a 70 centimeter band with a pretty standard TNC setup could have got our packets and got data for us and participated.
Yep.
So who knows how that affects the mainstream CubeSat industry, and who knows? I really don't know.
Yep. In fact, I was and will be once again set up to receive on that sort of thing. We're moving to a new facility here in about 2 or 3 months, and it will include a tower with a rotator. So
Yeah.
putting a couple circular polarized antennas on it for 70 centimeter and 2 meter will definitely be part of it.
That's actually something I wanted to talk to Patrick about when he gets back. Is one of my first. I was involved in a ham station at our university in a volunteer group for at UAH for about 6 years. And one of the very first things we did, in fact, the first day we set up our ground station, we had our rotator up, we had our 2 meter and our 70 centimeter antennas up from M squared. Is we got our first digital packet from the space station, and pretty much the second thing we did was Moonbounce, and we talked to Arecibo off the face of the moon. And for me, that was a huge motivator, and that was very early, and I ended up reinventing what we did in that lab. But quite possibly from an education perspective, I think he hit a really good point. about it was cost effective, but it was spectacular exposure and an experience of a lifetime for almost no money, relatively speaking.
Yeah, you know, I realized my interest in ham radio and space came from my dad's effort on Moonbounce, you know, many, many moons ago.
Yeah.
And it's really ironic because he heard via ham radio that the Apollo 17 was going to be the last one, and it's because of that that we did a screaming nonstop run across the country from Montana to Florida, and I was able to watch that last Apollo launch in person, and quite frankly, a little bit closer than we were supposed to.
Wow. Cool.
Yeah, that was one for the books. I really wish we had all the equipment that we do now to record and to share, share across social media back then, because this was something that I regret that I was the only one to experience.
Yep. The exposure to real-time events right now is very enabling.
Exactly. And
here in Huntsville, there's a lot of retired and a lot of passed away guys that have, or engineers that were participated in the Apollo program.
Mm-hmm.
And with that, they leave behind some great content, and a lot of that's been collected at the university library. And one of my brother's research topics, which was presented at the International Astronautical Congress, I forget which one, potentially the one in Beijing, but who knows, was about the digitizing of the film footage. And right now, if you go to any library and find this content, most likely the tape is somewhere in its last 5% of life just due to natural degradation. So it's really important that we get that content digitized before it disappears.
Absolutely.
Now, what lessons learned can come from that? Who knows? I mean, they had everything from launch videos to rovers driving around the moon, and a lot of engineering, a lot of sciences, a lot of microgravity sciences, and who knows what scientific results could be gotten from that data using modern technologies, or maybe a different hypothesis on the same experiment, and maybe able to come up with some other content. Who knows? There really is a lot of content that's sitting and probably will never get used.
Well, yeah, and it's funny because if you review research material of any kind, there is the opportunity to make a discovery. And to be blunt, if we're not going to budget our way back to the moon anytime soon, we need to be looking at that footage, because otherwise, you know, if it's lost, not only have we lost what we have done, we also lost the opportunity to do the research and to sift out new information and new data. You know,
Yeah.
I think there was one, I'm not sure where they left it, but there was a junior college here in Colorado that my daughter attended. They were doing motion tracking of the particulates from the lunar rover's wheel. Yep. And measuring particle density, and with the known of the gravitational constant of the moon, and with a known velocity of the tire, they could watch the arc and calculate the particle density and also particle size.
Wow, that's cool.
Yeah, so there was a lot, and the funny part is they identified the fact that there were multiple types of particles associated with it, and were able to identify the relative density, and thus, identify the difference between silicates, metallic objects, and they were able to observe the different strata that they drove over. It was the coolest thing I've ever seen. And that's all based on the old information.
Yeah.
That's just rehashing the old information, and grabbing some new stuff. They were using computer vision to do it.
Kind of bringing it around here, I kind of want to, Eric, you were mentioning that the low cost of entry for space comms is what enables it to happen, and what makes an easy and viable activity. The question is, if you want to do it on a professional grade or commercial grade, do the costs that Patrick cited in the presentation, and do the costs line up? And second, kind of, if you will, rephrasing a bit the question I asked Patrick earlier, from what you do of Spacecom's Radio Bro, what's the intrinsic market value of such a station, and is it able to turn a profit against the costs of running such a comm station?
I think that you have to consider, whenever you look at the business case behind it, you have to consider what's the market, what's the capability, who's going to use it, and whatnot. So if we go look at, from a mission perspective, what kind of missions do you have? Well, classically, there's only a few examples of a business case in spacecraft, and that's probably communications and imagery. Beyond that, it's probably more research. Do you guys have any other suggestions for more mainstream in space applications that actually are profitable?
There's when you look at Iridium and Orbcomm, they relay a lot of telecom and sat phone data, but it's also that with the upcoming Internet in Space project and what Google and SpaceX are engaging is where the revenue happens, and what's been driving Iridium and Orbcomm to be put up is the fact that the network is expanding, the increased capabilities need to be upgraded, and satellites have a limited lifetime. So therefore you see oh, hello, Mr. Barnard. You see where the profit margin of such a business is basically from the base telecom users, DirecTV, Sirius Radio, and others, as well as the fact that the hardware needs refreshing and upgrade periodically.
So I think you won't find as much of a business case as you may want in purely providing comms to a mainstream let's say a high dollar long-term customer, because that person will probably figure out in their business plan it was smarter for them to build a station because they're going to have, as a service provider, let's say a multi-decade program. So that's profit margin that they're going to want to keep because they're going to effectively build, either they're going to pay for you to build a facility and then expire its full, over the process of those several decades, they're going to expire its full life. And then you're going to take in profits, or they can take the profits. So I don't know that you can build a facility and then somebody will show up and want to contract you for a while. So I don't know if it's a reason to keep the doors open. It would be a hard sale. I think your market's going to be more short-term projects that are less than 2 years.
Mm-hmm.
And the issue I see with that is that the profitable spacecraft industry is not short-term. It's communications and imagery. Though a spacecraft may only be up there for 2 years, for let's say a LEO ComSat or a LEO imaging sat, they're going to put another one up in 2 years, so the ground station will need to run for 2 decades.
Yeah.
For example, so it's going to be hard to know if you could actually launch a business case to support those kind of missions.
Yeah.
Now, there is, I think, another twist that has the potential for being viable. If what you are doing is effectively having a current deployable set of control electronics, effectively remotely managed, point of present system, and your particular communications dish can be part of a what amounts to being a ad hoc interferometry group. there's a series of potential applications that start becoming possible when such ad hoc arrangements are made. In the past, it's been done really on a special purpose, one-off sort of deal. But if you could find a way to um, bring the costs in such that there's a reasonable control bar that could be met to allow the ad hoc aggregation, I think there is a potential for some value as to whether or not that is, a credible, profit center in and of itself is not entirely clear, but it is a step outside of normal comlink support.
Yeah.
Kind of a question on history here, because Patrick, he cited in his slides the network of ground stations that do exist, and as I understand Spacecoms back in the early Mercury and Gemini eras, it consisted of a series of ground stations communicating with orbiting capsules, and slowly was phased out and eventually replaced with TDRS and orbiting assets. The question is, if the argument for tonight was that ground stations have a lifetime investment advantage over satellite that has to be replaced every 6 months or so many years versus just a simple facility on ground that's always going to be there for the most part, why then did Spacecom start to transition away from the ground station format to the TDRS infrastructure?
Well,
Expensive.
yeah, the other thing was that, the first thing is that, just a slight clarification, the network of ground stations didn't come into its own until the last bit of Gemini. In fact, it was deployed in preparation for Apollo and for leaving Earth orbit. For something that's leaving orbit, it became very, very, very important to be able to shoot outbound. When that was no longer a national priority, it was much easier to put something into a fairly high orbit and gather a large swath of the Earth and of low Earth orbit using TDRS and others. This allowed also a larger number of ground stations that are not exactly ground stations, but satellites on orbit for essentially the same price as the large satellite ground station without the security issues. About half of your manning for a ground station during the Cold War years were your security, and there was other costs associated with all your logistical costs and so on. While you could put something in orbit, have multiple units that were multiply redundant for a much lower total cost of ownership over the lifetime of the system.
Okay.
But it only works if you are below the assets. Otherwise, you're going to be swinging the dish, through past 90 degrees, plus or minus. And so if we were doing Apollo today, like SLS is supposed to do, TDRS won't help you a bit.
Okay. Little question from the audience here. Luis Gelinas has posted in regards to what you're saying about regulation regarding communications. So why not operate in a country that is a little more law-friendly to your needs?
Mainly because we are subject to those laws no matter what country we're in.
That's right. Yeah, the regulations you have to abide by are I believe of the satellite manufacturer, not of where your launch location, but where the satellite's country of origin is.
Correct.
So, for example, if you have somebody in France launching from Russia or whatever, they're probably going to have to follow their regulations from France. Now, of course, Russia has the authority to launch them or not, so that's where you end up with your international partnerships. So the U.S. market is prohibited from just going somewhere else and launching and not following the rules. They're still having to follow all the U.S. rules.
Yep. Yeah, actually, what it actually boils down to is that you have to follow all the rules, and since it's all a blacklist, meaning that you, instead of these are the things you can do, it's more of a these are the things you can't do. And when you superimpose all those blacklists of every country, the countries where the ground stations are, the countries where the launch provider is, the country of origin for the satellite and the radio equipment, by the time you stack all those, there's a very narrow area, very narrow band that you can actually use. There are several narrow bands, but the U.S. is actually quite forgiving as far as what we're allowed to do compared to others. But the truth of the matter is that the bands we are allowed to operate in the U.S. are, with a very few exceptions, most of them being the ISM band, 900 and 400 megahertz in the EU, and UHF frequencies, are almost universal across the board.
Okay. All right.
Sorry, guys, would love to have that solution. Just go somewhere else, but.
All right. Well, we're coming up in the last 4 minutes of our broadcast, but kind of a question in closing to ask the panel is, what does the future of space communications look like? What will we use it for, and what kind of businesses can be supported by it, as well as what businesses can grow thus from using SpaceCom?
Ooh, good question.
You want to know the scary truth about that, Ethan?
Yes, please.
Here it goes. It's all going to be laser comms. You can go megabit for less than a watt, and you can talk a long way.
Oh.
I will agree conditionally.
Expensive technology.
Yep, laser comms work great, but it is not always clear. If you are occluded by clouds, your lower frequencies are still reign supreme. As far as the future, we're probably going to be seeing higher frequencies being in use more often, including optical communications. Ka, Ku band being two of them. But for to a large degree, I don't think we're going to walk away from UHF or even VHF. Those are still going to be the old standbys. It's like today you can still find Morse code on the ham radio bands, even though it's no longer something that is tested. It's just that at the much lower frequencies and for distance communications and for low power, it reigns supreme still.
I think there's going to also be a broadening of who's involved with respect to KA systems. I think you're going to see, dramatically, smaller and more accessible optical systems, but they are, inherently more directional. I think you're also going to see, larger scale platforms on orbit that are going to be, set up, with plug-in and plug-out transponders. I think that you're going to see far more of a combination of both the ability to do narrowcasting and the interoperability of systems. I think we're heading towards an environment where you're where satellite communications is going to be much closer to a automated telco network than a what has been frequently specifically engineered single purpose comlinks.
So you're talking about turnkey solutions then?
You're basically, I guess the classic example is right now even things like the TDRS are still highly manual in terms of the scheduling process, and they're frigging operating in a bent pipe mode. Okay, and as such, they're highly wasteful. Of their available bandwidth. I believe that what we're going to effectively transition to is the ability to do dynamic scheduling of satellite assets, much like you can have dynamic allocation of switches, automated switches in the telco network as exists on a terrestrial basis. I think we're going to see far more. I think we're going to see a transition to quality of service based routing for satellite through systems where satellites effectively become an additional part of the network for conversations and data transfers that warrant the ability to deal with delay or disturbance tolerant networking situations. So it's a different, an evolving market, I think, if you will.
All right.
Just to agree with Gary here, imagine today we reach in our phone, we reach in our pocket and grab this. We don't worry about making the physical radio connection. We don't make sure that we're on the same band as the tower. We don't manually kick in the correct encoding and so on. We pick up the thing, dial the number, or choose it from the list, and hit the little green button. It's a turnkey. That's why I mentioned that. I can see as the technology becomes more ubiquitous and more mature that this would indeed occur. Another thing that we're probably going to see is as we go higher in frequency, we're going to see a shrinkage of the components for the same amount of bandwidth and gain. I can't divulge a whole lot of details here because I'm still dealing with the Commerce Department on it, but I can give you guys a sneak peek. Here's a Ka band transceiver with integrated flat panel antenna, and it's not very big. Still working out the details, but it certainly is within the physical dimensions of a CubeSat. And so when it comes to ground stations, I can see ground stations becoming more compact. I can see ground stations, instead of having a Cassegrain or a direct focus dish, becoming a flat panel or phased array. And eliminating a lot of the wind load. But yes, Gary, I 100% agree with you. It's going to become more turnkey, and that would mean that a lot of the satellite ground stations are going to be about as manned as the current cell towers are, which is to say they're not unless there's a problem.
Right. And when you transition to being able to have a ubiquitous deployment of software-defined radios, okay, it just adds to this notion that you're creating a pervasively networked environment where you're continuously saying, okay, who can I talk to? What are the rules? And as a consequence, I think what you're going to have is a whole series of overlays of ad hoc networks, where what you're transitioning to is what one might consider virtualized functions. Okay, for there's a if you want to set up an interferometry play for a particular mission, you can effectively have an app that can be deployed across there's a bounty. Hey, if you'll participate in our allow your rig to participate in our interferometry experiment, okay, and you sync up to you sync time, and you activate within these time frames. You get a bounty for participating. Okay, there's a whole the whole notion that you can have a not just a bartering value, but there may even be a monetizable value for participation in ad hoc networks that enable you enable basically functions to be virtualized.
Yeah. Kind of a quick question here. Mr. Gary Bickford here is asking Aaron, is that a fractal antenna you just held up there?
That's the nature of the problem. It's actually a derivation of phased array. I guess you could call it fractal in that it has the elements of varying wavelengths in a geometric pattern, tessellation, so to speak. But it's not. It's more of a phased array. In fact, it resembles aircraft radar, the flat panel dishes that are in modern aviation now. Can't really. I'm being kind of hedgy here because I do not have export control blessing. Nobody has said, "Yea, verily." You can share this with the planet, but it's nothing spectacular. It is very, very, very frequency dependent, though, and in that way, it's very different from a fractal antenna. Being that a fractal antenna is a fairly broad bandwidth, this one is very, very specific.
Okay, thank you.
By the way, Gary, you were talking about modules and software-defined radio. Just to give you an idea of something else the future holds. Let's see, where's my screen share? There it is.
Yeah.
This is a software-defined radio system that is a bunch of blocks. This is GNU radio, and for example, you could take a Fourier analysis and put it out on the field, and then connect it like so. Well, actually, no, that's a different type of thing. But you get the idea. You can just basically move blocks around and connect them up different ways. When it comes to making a experiment, it might be something that we do remotely using sort of a web interface, and in so doing would become a things that multiple people can work on things. And with a phased array like what I'm doing here, it can identify multiple points and communicate with them. It can split the antenna, sacrificing a little gain. It can focus at multiple points. For example, doing a switch over to another ground station, or doing some radio science with it. So there's your future.
Gary, quick question for you, because regarding the future, Mr. Gary Bickford also asked you, your remarks raised the question, will all those dishes you cited become obsolete for the new technologies you envision coming up for space comms?
It's interesting. The world of big dishes. There's needs for some of them. Okay, and how many is an interesting question. NASA was faced with that, and they concluded that given a choice between having one more 70-meter dish, or 436. I guess it was 436-meter dishes. They went for the 436-meter dishes. Okay, you end up in a situation where there's got to be a reasonable match to the technology. Where things are going with respect to laser comm with LADI, the recent lunar laser communications experiment, that was about an 18-inch cube. Was sort of circumscribed what the system was. They weren't worried in particular about mass or volume when they did that. The folks that did that, when asked as to whether or not they could fit the same and down to a 1U factor, their response was they'd love to try. Okay, they hadn't found anybody that was willing to pay for that yet, but they would really love to try. You're from a receiving end, again, for optical, it's not very big. For the world of other frequencies, I think Aaron's right. We're heading more towards phased arrays, tunable. An awful lot of what we've seen in the way of receiving antennas has been purpose built for specific frequencies. I think we're going to see a lot more tunable arrays because what you're going to want to be able to do is understand all the available signals out there that you may be able to latch onto and differentiate and be able to pick what's appropriate to task at the time. It's going to be so. As a consequence, there'll be an awful lot of old iron that will be scrapped over the years. But it is to the extent that we can retrofit it with adaptable equipment. I think there's some incredible assets there to take advantage of.
Mm-hmm. Okay. All right. Well, we have time. We're coming up here on 9 o'clock, but we have one final question, and I suggest we close after this. This is for Mr. Harper from Mr. Bickford. Not sure if this is appropriate. We'd like to put some useful information about ITAR and the related information discussed onto the Integrated Spaceplane website. We would like to talk with Mr. Harper at some point.
That would be fine. I'm glad to do it. Most of the information that I presented is discussed and publicly available on the Mach 30 website, mach30.org, and it's a nonprofit with open meetings. So all the meeting minutes are publicly available, and a lot of our efforts, we were part of the export control review process, and it's something that we're constantly working forward because, frankly, we believe that space needs to be open. It needs to be a person needs to be able to develop and repair things in an open form, not in a closed form. And the main objection to that is ironically not industry, but rather government and export controls, and that's why we're here.
All right.
Also, there are several gambits with respect to ITAR compliance. There is the the cross between one gambit, of course, is the open source slash public domain route. Okay, which if you're willing to do that, there's a path to dealing with such issues that way. There's a second route which might be euphemistically referred to as the academic one, where if you're willing to tell people what it is that you're going to work on, you work on it, you present at peer-reviewed conferences, you write papers, which are peer-reviewed, and you basically you research and publish. That is another path, which a number of research institutes and different universities have taken, as a way of dealing with ITAR. There is a third path, which is you lay out in advance what it is that you're doing, okay, and it's euphemistically referred to as the no surprise path. For example, that's what CAISP Inc. has done with the sitting down with the State Department representatives saying, hey, this is what we're working on, and this is exactly what we're doing. Okay, and the response has been, okay, that's fine. Okay, so long as you don't surprise us, we won't surprise you.
Yep.
All right. Well, we're coming up on 9 o'clock, and I believe it's time for us to close. But, gentlemen, thank you very much for joining this panel and to our audience for participating for this. This is the close of the 8th Global CAISPN call for space communications and business models. Thank you to Aaron Harper of ISIRU, Eric Becknell of Radio Bureau, Gary Barnhart of CAISP, and Mr. Patrick Bartholow of Team Synergy Moon. I'm Ethan Chu of CAISPN, signing off. Good night.